Friendship groups, ensembles in machine learning. Is there any difference? They seem like they're entirely unrelated concepts, but there's actually a very deep connection. And it's a deep connection that I've been realizing and researching lately in the AI space. This video will focus on the key concepts and the intuition behind this. It's to act as like a survey video instead of like an in-depth or mathematical ones, because those will come later. So we'll just survey it in this case. Let's start with some basic social psychology. What is a dyadic friendship? A dyadic friendship, or a dyad for short, is a friendship structure that consists of just two individuals, so one-on-one basically, you and someone else. As you can clearly see, this dyadic friendship is obviously very intimate then, because there's only two individuals, two members. It's characterized by reciprocation too, so like you return equally as much as the other person, typically, in general, that is. But there's also a subtle problem. For all its depth, there's also a dependence issue in the sense that there's a risk of becoming overly reliant on that other friend, because and you become too reliant on it and too dependent on their emotions, thus causing some kind of volatility. Uh, this is called the co-adaptation problem when we translate that to machine learning terms. In neural networks, which power ChatGPT, neurons often become over-reliant on other ones and those sort of co-adapt in a way. And that makes them perform weaker because they are dependent on others and not able to think freely. To counter this, researchers proposed something called dropout. Dropout basically, for all the neurons in the neural network, they randomly drop out or like shut down neurons like randomly based on a certain probability so that no neuron can become overly reliant on another in case it will just like magically shut down in some way. So they have to think freely. And what I'll discuss later in detail is that we can see this as sort of an implicit ensemble. But that's for later. Shifting our eyes back to psychology, we can discuss the friendship groups. A friendship group is a structure consisting of three or more individuals. So, as the name suggests, it's a group. In this case, there's distributed emotional support because there's many people you can consult and all that. And then it's also very resilient because if one person leaves, the whole friendship group doesn't really, well, it takes impact, but it's obviously not catastrophic. Unlike if there's a two-way friendship, if one of them sort of leaves, then most of it's gone. So it's very resilient to these stuff. Hierarchical structure of friendship groups is another point, in the sense that most friendship groups also have some kind of hierarchy in the sense that one individual might have a certain social status, someone might be disregarded, someone might be very popular, etc. So this hierarchical structure is what characterizes friendship groups. There's also a sort of popularity bias to it, because in most friendship groups, the people at the top of that hierarchy receive most of the attention. So that's one concept that is key to machine learning too, which we'll discuss the connection in a bit. So breadth and depth. These are two sides of the dilemma, basically. A dyad prioritizes depth. We want the connection to be as deep as possible, whereas a group prioritizes breadth. So it's how many connections you have. So it's about quality versus quantity, basically. So which is better? Well, socially speaking, that's up to you. But in machine learning terms, we can sort of debate on this in modern machine learning, and it's becoming increasingly prevalent everywhere. Just as a preview, neural networks, there's often like a debate on whether deep neural networks are better or wide neural networks are better. Obviously, I'm not explaining the whole thing here, But basically, what happens when you take an infinitely wide neural network or an infinitely deep neural network yields something called kernel regression. So this theory of kernel that an infinitely wide neural network is kernel regression is often called neural tangent kernel theory, or NTK for short. But that's way out of the scope of this video, so let's just focus on the variance of friendships. In general, friendship groups yield lower variance, so it's much more predictable and it's more stable, generally speaking, because there's actually a proof for this. If we assume no correlation, the friendship variance of a friendship group is the individual variance divided by n, where n is the number of individuals in that group. If we assume correlation, of course, this changes, but let's just assume this idealized case for simplicity. So we can see that friendship groups are more resilient and more stable. And this whole philosophy is founded on something called the wisdom of crowds, which states that if you have a lot of people, thus crowds, they can make more informed decisions, more accurate decisions, and you're not all over the place. And it's quite true. And it's the assumption that underlies modern AI ensembles, what we call them. So let's connect this analogy to machine learning. An ensemble consists of k models, where k is like the number of models, obviously. And a friend group consists of k friends. Can you see the connection? An ensemble is basically like a friendship group, but in machine learning. And variance is similarly reduced because there are more members and thus it's more resilient. I'll show you the mathematical proof in another video. But often, if you have a very, very large friend group or ensemble, it becomes very, very computationally expensive, basically. So one way to counter this is a specialized kind of ensemble called mixture of experts, and it's a very, very, very hot topic right now. And it's how modern AI systems like DeepSeek, ChatGPT actually become scalable. So most large language models are based on this architecture, the mixture of experts. The core idea is quite simple. Instead of one monolithic giant model, like just one really big model, we deploy k mini and domain specific models. So instead of one giant model, we have a bunch of small ones. And the assumption behind this is that these small ones are each better in their domain, in their specific domain, than an overall giant model. So it's like generalist versus specialist, right? Jack of all trades versus master of one, right? These experts might be able to defeat that one giant model in one specific domain, in one specific area, but it's not necessarily true for like in general, right? But if we combine many of these domain-specific experts, each specialized in their domain, this can often rival the quality of one generalist model with significantly more efficiency, because only some experts are actually run at one time. The one that is decided by something called a router. And basically, the router it takes a look at the task at hand and takes a look at whether it's like biology or whether it's math or anything, and then takes a look at the experts now, takes a look at those specific mini models, and it asks the question, which model will be best suited for this task? If we bring this back to our friendship groups, a router basically takes a look at a specific task and asks which friend is best at that specific task and asks that friend, only that friend, to do that instead of the whole group having to waste their efforts doing that when the expert or specialist of that specific task in the group can just do that. For instance, if one friend in the group was good at, for instance, writing or talking or something like that, then for a talking task, only they would be appointed. The whole group doesn't need to waste their efforts to do that. So instead, that's much, much more efficient because instead of having to do the. So as you can see, it's like much more efficient. But there are obviously a lot of problems with these structures, friend groups, and mixture of expert models, or MOE for short. One such problem is called the resource allocation. And it basically asks, how do we fairly divide all these resources, for instance, like money, efforts, or workload, among these group members to be fair? We want to sort of allocate these resources fairly so everyone gets it's fair, basically. One social economics concept of this is called Nash social welfare. And I won't dive into the mathematics in here because I'll save that for a dedicated social science video. But basically, it utilizes a product. And basically, this product can sort of balance it out because if you have a low number on the product, then everything gets dragged down. And if you get zero on a product, then the whole thing gets zero. So it's very fair. Basically, accounts for everyone else's needs. It's a great way to model how the uh, friend groups are fair, basically. Credit assignment is another issue, and it concerns who did what. Imagine you are doing a task and you want to figure out how much someone contributed to that specific task. Credit assignment asks about like how much influence each person had on the final result, and thus can accurately assess uh, how much reward you get, basically, and figure out who did what. The final issue is called router collapse, and basically we can take a look at that from our analogy of the friendship groups and think about popularity for a second. Popularity bias is basically if someone is very, very popular, built on years of reputation in the group, then they'll naturally get selected for more stuff, right? If this mixture of experts is like um, deciding who gets to do what at a specific time, well, then it makes sense for the router to choose like the most popular person, right? Because obviously it's more likable in the group. In machine learning, that's the same idea. And that's one of the major problems with mixture of experts. If one expert is popular, for an instance, or just performs really well on a specific task, then it builds that kind of reputation, and the router just learns to sort of direct everything to that specific model. So it ignores everything else, biased by popularity, and thus it doesn't really become much of a group work anymore, but rather like just everyone sits there and one person does the rest. So it's like those teamwork activities in high school where someone takes over the whole thing and no one else does anything. That's probably the best analogy I can put it as.